Hi and welcome to this session on problems from chapter 42. The first problem we're going to be tackling is problem 52. Again, we're going to follow the same method as we did last time, in the sense that we're going to do one problem, then pause, and then another problem till we cover at least, maybe, I'm hoping 4 or 5 problems at least from this chapter, maybe more. Okay, so the first problem is problem 52, and it's a challenge problem. So what it is it gives you so problem 52 first. Why do we have this color? Anyway, in this problem it says a colorless, odorless gas in a tank needs to be identified. The gas is either nitrogen gas, N2, or carbon dioxide, carbon monoxide, CO, or nitrogen oxide, NO. So we know it's a diatomic gas, basically, one of the three. Okay, and white light is passed through a sample to obtain an absorption spectrum. So we're going to have an absorption spectrum, basically missing lines. Among others, the following wavelengths present dark bands on the spectrum. So they are missing. So the wavelengths are lambda, given by, they're giving you a lot of sig figs in here, 4.2680 micrometer, and then 4.2753 micrometer. They're all in the infrared region. Okay, they're not visible. 4.286 4.2826 micrometer, and 2972 micrometer, and the last one is 4.3046 micrometers. So those are bands that are missing from the spectrum. Okay, arranged from shortest to the longest wavelength, basically, meaning the most energetic to the least energetic one. So what photon energies E correspond to this wavelengths? Specify your answer to 5 significant figures. Note that the speed of light C, so we need C now because we really have to get this expression with this many sig figs. So the speed of light is not 300,000 kilometers per second, but it's 2.9979 10 to the power 8 meter per second. Okay, and the H in this case, we're going to be using electron volts, so instead of joules it's going to be defined as 4.1357 times 10 to the power negative 15 electron volt times second, not per second. Second, it's an action, it's energy times second. Okay, so we need to find E, basically. Remember E from way back, it's related to the wavelength for an EM wave as being hc over lambda. So we have 4 values, so basically all we have to do is get this calculator and start plugging numbers in it, and that's it. So let's start the first one. H is, so I'm going to use just one formula and basically keep on changing the wavelength, and that's it. So E, it's going to be from high to low because lambda is ranked from low to high. So again, 4.1357, oops, I left it, 10 to the power negative 15 times the speed of light, which is 2.9979 10 to the power 8 divided by, open parentheses, the first wavelength in here. Oh man, it's not even moving. Okay, so the first wavelength is 4.28 2.6 42680 10 to the negative 6 and close parentheses. So this is basically the first energy, and it is 0.29, so we need 5 sig figs. So the first energy is 0.050. Okay, I rounded up. Okay, electron volts. The second one, all I have to do now is copy this formula basically and change the wavelengths. So the next wavelength is 4.2753. Okay, same units in there. Okay, the second one is slightly less energetic, 0.29, and there are a bunch of zeros, so 0.000 electron volts. Okay, and the third energy is going to be divided by that same frequency, so I'm going to get the same formula in here, but the wavelength now is 4.2826, so it's 2826, and this is 0.28951 electron volt. And the last two, I have actually the book in here. The fourth one is 2972. Everything else is the same. Is 0.28852 electron volt. And the last one corresponds to a frequency of wavelengths of 4.3046. Okay, and that's the least energetic one, 0.2880. I'm gonna round it up to 3 electron volt because we need 3 sig figs. So those are the different energies for each and every one of those wavelengths that have been emitted. Okay, these represent transition from the lowest rotational energy states to okay, so find the energies, so make sure it's 5 sig figs, so we did that part. B, which one of the absorbed energies correspond to a transition from an energy level of an L equal to 0 to a state L equal to 0 state of the gas? Okay, use equation 42.9 with the transition rules as a guide. Okay, the transition rules from basically the selection rules, if you guys remember from the previous chapter, is the change in N has to be 1. Since we're going from lowest to highest, because this is an absorption spectrum, so N has to increase by 1. So if the initial energy level is N, the other one is an N plus 1 transition. Okay, so that is one thing. The other rule is that the change in the angular momentum must be either plus or minus 1, so that the photon that is emitted will carry with it that momentum. Okay, so we have several possibilities. This energy levels, here is the thing. We need 5 of them because we have 5 lines in here. Okay, we have 5 lines, so we need to find them all. So the first energy level, N, this is N plus 1, is going to have the lowest energy level in this case corresponds to L equals to 0. In this possibility, the only way to go for, in the case in here for N equals to N plus 1, then we also still have N equals to 0, but we also have to have an N equals to 1 at least. I mean L equals to 1. This is L equals to 0. Now, here is the deal. If I want to go from 0, the only place I can end up with is this one. Okay? So So this is the first energy level that satisfied the condition, the selection rules that the change in n is 1. We went from n to n plus 1. And then also, in a sense, we increased n by 1, L by 1. Okay, so that's one possibility. So that's one of the spectral lines that we have. The other possibility then is for L equals to transition from L equals to 1 in the energy level of n. So in that case, we can go from L equals to 1 to L equals to 0, and that is possible too. Okay, so that's another line, because we changed the n by 1, and we also changed the L by positive or negative 1. So in this case it was negative 1. So the other line that we can go to from 1 is actually going to be in L equals to 2. We cannot go to L equals to 1 because that's not going to be good, because that's going to result in a delta L that is equal to 0, and that does not conserve angular momentum. So in this case, that is the third transition line. So we still have two more to account for, and that goes from L equals to 2. From L equal to 2, we can only end up at either L equals to 1, that is the fourth line of those that are listed there, or we go to all the way to L equals to 3. We cannot go to L equals to 2 again, or even L equals to 0, because then that corresponds to delta L equals to 2. So this is the 5 lines that we're looking at. Okay, so we want to know, we want to rank these transitions basically in terms of the least, I mean from the highest to the least energy, and that is where we're going to find which ones they are. Okay, so the question is, let me read the question again. Which one of these transitions corresponds to from a transition of L equals to 0? Obviously from the schematic, L equals to 0 goes to L equals to 1, clearly from that picture in there. So let's look at the expression first of all of E, N, and L that we found last time. It's L plus 1. That is the formula that they tell you that you're going to be using, times H bar over 2I plus N plus 1/2 H bar omega. Okay, now, well, if we do a delta En between each and every one of them, basically going from all of these transitions, we're going to be computing delta E from N to N plus 1. This part is going to give me the value N plus 1 plus 1/2 minus N plus 1/2 times H bar omega, and so this part is going to be H bar omega. So this part is going to be strictly H bar omega, because of the fact that everything is the same. So this is H bar omega. So the change in this case in the energy will go from 0 to 1. So it's going to, what matters in this case is this value in here to compute it. All of them, they're incremented by H bar omega from the other one. So this is the different energy. So I'm going to label the first one. The first one is going from 0 to 1 in terms of the energy. So it's from 0 to 1. In this case, the change in the energy is going to be the following. The final state is 1. So we're looking at this one. Okay, the final state is 1. So it's going to be 1 plus times 1 plus 1 times H bar over 2I, which I'm going to take as a common factor, H bar over 2I. Okay, and minus the initial one is 0, of course, times 0 plus 1, which is 0. Okay, so in this case it's going to be 2 times 2 divided by 2, so it's going to be delta E01 is going to be clearly equal to H bar over I plus H bar omega. Okay, did I include an H bar or H bar squared? I think it's an H bar squared. I made a mistake here. Okay, so the contribution is a minor contribution, relatively speaking. Anyway, so let me look at the, make sure that I'm using the correct formula. I think it's an H bar squared. Yes, it is. Where is it? Yep, yeah, it is. It has to do with the kinetic energy, basically, of rotation in this case. Okay. So this is one of them. So this is one of the 5 energies that we're looking at. I need to look at the other energy. Of course, we're going to compute this one and see which one is among this one is that value. In other words, we're going to rank these values, these 5 values in here, and see where it sits in this 5 values. Once we find it, we say, okay, this one or that one or this one is the correct value. Okay, so the second energy that we're going to be looking at, I started labeling them, is from L equals to 1 to 2. So that is delta from 1 to 2. This is, I'm keeping track of only the change in L, okay? So in this case, it's going to be the same thing, except that the final is 0 minus 1 times 1 plus 1, which is 2, times h bar squared over 2I, plus the same quantity in there, okay? Omega, by the way, is equal to square root of k over the reduced mass in this case, okay? So, I have in here, in this case, it's going to be the same thing, except it's minus h bar over I, omega. H bar, plus h bar omega. Okay, here is the deal. This energy level sits below this one. So wherever we find the first one, this one is below it. So if the first one is here, the other one is somewhere, one of these 3. Okay, so this is not the lowest one of them. This is potentially is the lowest. Let's look at some more. Okay. The transition 3, okay, from 1 to 2. So now it requires a little bit of calculation. So the final one is 2. So delta E from 1 to 2. Then this will correspond to, again, the final one is 2 times 2 plus 1 minus 1 times 1 plus 1. The whole thing, h bar squared over 2I plus h bar omega. Okay. This is 2 times 3, that's 6, minus 2, that's 4. 4 divided by 2, that's 2. So this is a positive h bar squared times 2 divided by I plus h bar omega. So far, this is the highest of the 3 of them. Let's look at another transition in here. 3. Let's look at the number 4. Number 4 is going from L equals to 2 all the way to L equals to 1. So from 2 to 1. Delta E from 2 to 1. Okay, so the final state is 1. That means 1 plus 1 minus 2 times 2 plus 2 plus 1. Okay, the whole thing is h bar squared over 2I plus h bar omega. Okay, here is the deal. You have 2 minus 6, which is negative 4, divided by 2, that's negative 2. So this is actually the lowest so far of all of them. Okay, h bar omega. The last transition that we can clearly see from here is going from L equals to 2 all the way to L equals to 3. And that is going to be delta E from 2 to 3. The final one is 3. 3 times 3 plus 1 minus 2 times 2 plus 1. And this thing is multiplied by h bar squared over 2I plus h bar omega. H bar omega is coming from the vibrations, by the way, so that you guys are... So 3 plus times 4, that's 12, minus 6, that's 6 divided by 3, that's 3. So it's a positive 3 h bar squared over 2I. I'm sorry, the 2 is cancelled with the 6. Plus h bar omega. Okay, so this is the highest one. So this is the highest energy. So this is from 2 to 3. For L, that is. Okay. And the next one in height is going to be from 1 to 2. So this is from 1 to 2. Okay. And the next one that is going to be, where is the h bar? So that is from the 0 to 1. So this is actually the one that they are asking for. Transition from 0. This is the 1. Okay. So the third frequency is from 0 to 1. So that corresponds to h bar squared over plus the other one. And then there is another one which is from 1 to 0. This is from 1 to 0. Okay. And the last energy level is going to be from 2 to 1. Okay, so we have them all. So the question is, again, which one of these absorbed energies correspond to a transition? from L equals to 0. From L equals to 0, it's the third frequency, the third wavelength, or the third energy. Okay. So the answer to part C is the one that goes with 4.2, 28, 26 micrometers. Okay, that is the one going from zero, because we know it has to end up in 1. From L equals to 0, that is. That's symmetrical state. Okay. Determine. So we're doing, see, which one of the absorbed energies, so we need to do, that was B, by the way. Part C is the one, which one of the absorbed energies corresponds to a transition to an L equals to 0. To an L equals to 0 is the one immediately below it in terms of energy. So that goes from, so this is the fourth one actually, and that would be, the answer for that is the 4.2, 2972 micrometer. Okay, so that is going to be an energy. Remember the computed values in here, so we need the energy. So this is to L equals to 0. Okay, so this expression in here is, how much did we compute it? It's 0.28951, 0.28951 electron volts, and the other one is the one immediately next to it, which is 0.28852. Okay, so this one, according to the spectra, the first one is an h bar over I plus omega, h bar omega, and the other one is the same thing. So this one is equal to actually negative, is it negative or positive? Positive h bar squared over I plus h bar omega, and the other one is negative h bar squared over I plus h bar omega. Okay. Part D, determine the value of h bar omega, basically. Okay, where k prime, so we're going to use that. So find the h bar omega. Okay, that's very easy. From this one, we have the sum of these two quantities, the difference of these two quantities. All I have to do is add this side and add this side. On this side, these two quantities will cancel, so I will be left with 2 h bar omega is equal to basically the sum of these two numbers. Oh man, do I have them in here? Yes, I do. I have them before the rounding, so plus, no, that's not the number. No, I'm sorry. I'm using this calculator if you guys are. Okay, so I know 5.1, here is the number. Come on. Plus, yep, the 5.2. So that is the 5.2. So that is 0.289, and I need the number immediately, this one, yeah. And that is going to be the sum of these two. So the this value in here, so h bar divided by 2, because we have to divide by 2 to find h bar omega. Come on. I don't mean to write it twice. Man. Divided by 2. Okay, so h bar omega, so it's just the sum of those two quantities. This yields h bar omega, which is half of that quantity, which is going to be 0.28901. Okay, this 5 sig fixed electron volts. Okay. Okay, so by the way, remember that omega we saw it is equal to square root of k over mr, where mr is the reduced mass. I know the book uses k prime, but I already distinguished that by using kb for Boltzmann constant, so that we don't have to keep track of primes and unprimes. So, determine the molecule's moment of inertia I. Okay, so we can find I by just actually subtracting this equation from that equation, because h bar omega will cancel, and we'll have 2 h bar over h bar squared over I is equals to this difference between these two quantities. That's why I guess they want us to keep track of so many sig figs, because if we round, then we will have a problem, because we will not get any quantity in there. So it's going to be 2h bar squared over I is equal to the difference of these two quantities, not their sum now. So where are they? So the first one is this one minus the second one. So I'm using, actually I'm kind of doing something that's probably not good, in the sense that I'm using the raw numbers, not the rounded ones. So it gave me this number, which is a very tiny number, and now I have to divide that. So let me write it down. 0.000938 or something. Let's call it in this case delta E. Just delta E, or just, let's call it E prime. Okay, just to confuse, not to confuse the deltas that we have up there. Okay, so it's clearly in this case I is just equal to 2h bar squared over that difference between these quantities, because this is just an intermediary value. In h bar, remember, it's expressed in electron volts per time a second. So let's get that number in here. 2 times 1,357. Okay, we need to open parentheses because we're going to square this number squared. So we better be ready for the squaring. 10 to the negative 15 squared. I think we're going to get something not correct in this case, because of the fact that we need to use the SI units. We need to use the correct value of SI. Okay, we have to use the correct value of H in here. I think the units are not matching correctly. Anyway, so we really have to use 6.26, 6.626, 10 to the negative 34, and divide that by 2 pi. Okay, and divide that by the energy, which is this much, which is electron volts. So we need to time that. 1.6602 times 10 to the negative. All I'm using now is using the proper SI units. Okay, getting back to the value on joules, and okay, so this is the value now. So that's your. So I converted back to the SI, which is the correct value for each bar, which is just h over 2 pi, and then I converted the energy difference in here into a proper joules. Okay, so when you get that, the answer is 1.4115. This is 5 sig figs times 10 to the negative 46 kilograms meter squared. That's the units for, because that's why I wanted to be careful in here in terms of units, because I want to find the moment of inertia in terms of kilogram meter squared, which is a proper unit for it. The atomic masses and the bond lengths for the 3 molecules options are shown. So they basically give you 3 pictures in here for the nitrogen N2. So each one of them has a 14, basically the mass number of 14, and the separation between them is 110 picometers. In the case of carbon, CO, you have 12, 16 and 12, and the separation between them is 118 picometers. And finally they tell you that the nitrogen 14 again combined with the oxygen 16 again, the separation between them is 115 picometers. Okay, so all we have to do now is calculate the moment of inertia every single one of this, and then we're in business. Okay, remember the expression in here has to do with the reduced mass. This is with respect to the central mass. So this is mR, which is 14 times the atomic mass. I gave you that being to be equal to 1.6605 times 10 to the negative 27 kilograms. So we're going to leave that until the end where we're going to sub 0.5, yeah. We're going to sub that toward the end with U. So the product of the masses, both of masses are the same, divided by the sum of the masses, both masses are the same. And this is U, that's 4, okay? Times the separation squared, which is 110 times 10 to the negative 12 squared. So this is the first one. So the second one is going to be the same identical formula, so I'm not going to repeat it. Basically 12U times 6, okay, I'm repeating it now, sorry. 12U plus 16U times the separation, which is 118 times 10 to the negative 12 squared. I'm going to calculate all three of them and see how much they are. It should be easy, straightforward. So again, I'm going to leave the masses toward the end. So I'm going to open parentheses 14 times 14 divided by open parentheses 14 plus 14. I know you're telling me, why don't you do it in your head? No, because I want to just sub the value in there later on so that I can do it faster. So it's 110, 10 to the negative 12, okay, squared. This is one time when doing mental math is not useful. Oops. Now I have to multiply by that U, remember? That U is 1.6605 10 to the negative 27. Okay, here is the deal. Because one of these U's cancel this U, and you will be left with just one in the numerator. Same thing in here. So you will only have one in the numerator. So if we do this calculation and we're careful enough, enter. So the first one is going to be, for this one is 1.4. Okay, they gave us only 3 sig figs in this problem. So technically we can only keep 3 sig figs in here. So 10 to the negative 46 kilogram meter squared. And that looks like it's very similar to this number. Let's look at the second one in here. Okay, here is the formula that I'm using, by the way. So all I have to do now is change the numbers now to CO. So this is 12, that is 16, so that is 16, and this is 12, and come on, this is not good. Okay, and the separation between them is 118. So this is actually 159. So this is not CO for sure. 1.59 times 10 to the negative 46 kilogram meter squared. How about NO? So we're going to change the same thing, except now this is 14. Oxygen doesn't change, that stays the same, so that is 14. The mass doesn't change, and separation changes. Separation is 115 actually, picometers. Okay, so this turned out to be 1.64. So it's actually N2, nitrogen. Okay, because it's the same moment of inertia. Okay, so it's nitrogen. What is the reduced mass, MR? Since we know it's iron nitrogen, the reduced mass MR, so we can find it. MR. Oh man, this problem is taking too long. It's just basically 14U times 14U divided by 14U plus 14U, and that is going to be 14 times, that's 28. So we can reduce this one by 14, and U is gone, and this one is left 1 plus 1, which is 2. 14U divided by 7U, and 7 is 7 times that, 1.6605 10 to the negative 27 kilograms. I'm not going to bother with the calculation right now, but you can do that kind of math in here. 7 times that number, so it's going to be something 10 to the negative 26 kilograms. So that is the mass of the reduced mass of the. Okay, the final question is, what is K prime? Okay, we know what the MR is. We know now what that quantity is. All we have to go back into this expression in here, since we know what H bar is, we know what omega is. So from here we can find omega. Omega is equal to the sum of those two numbers divided by h bar omega is going to be, I'm sorry, we already have this quantity in here somewhere. Okay. And then all we have to do is just basically, since we know what omega is from this expression, and we know what mr is since we know now it's nitrogen, so we can square this quantity omega squared times mr, and that's going to be exactly k. So I'm going to leave it that for you guys. You're going to find a large number, okay? And it's going to be in Newton per meter square per meter, yes, okay? So you're going to find omega, so that's basically what the last part in here. And since you know from this previous calculation what h bar, so basically what you did in here, you summed these two quantities and you divided by 2, that gave you the value of h bar omega. And now you have h bar. In this case, you don't worry about converting h bar. Use the h bar for this problem in terms of electron volt second, and you'll be fine because the electron volt cancel the electron volt and everything is going to be fine. So you don't have to worry about that conversion. And at the end, you're going to find omega. Once you have found omega, you square it and you multiply it by mr. Mr. Don't forget to multiply by the value of the conversion to kilograms. Once you have that, then you're going to end up with a value for k in Newton per meter. Okay, so this is problem 52. I know it's a long problem and it's one of the typical problems we do with the molecular transitions, and there will be more problems. So I'm going to pause right now. I'm going to take another problem and we're going to do it one step at a time. Okay. Okay, so let's resume with these problems. Okay, I think this video is getting a little long, so I'm going to go a little bit faster with the next few problems. So what I have in mind is problem 51. Also, oh man, changed pen colors again. So problem 51, and then problem 49. Which is an interesting problem. I'm going to do problem 47, but I'm going to defer it for you guys to do it because problem 47 is an all data problem, so I'm going to ask you guys to go through it. It's basically you have similar data that you're going to draw lines, and at the end you're going to plot and come up with conclusions, and we've been doing this now for a long time. Problem 44 is a similar problem that we have dealt with in the past. Basically this is where you find the minimum energy and so on and so forth, so for an ACL model. So you can do that on your own. I'm going to emphasize on problem 49, which I'm going to do extensively in here. I think that's going to be enough for right now in terms of the problems that we're going to do. Problem 38 is a very interesting problem, but I think you can handle that. And again, if you have difficulty with these problems, please let me know. I had in mind also problems 32 and 35. But that's the problems that I'm going to, for right now, do, because this thing is getting longer than actually needed. Anyway, so problem 51 also is a kind of problem that you might have encountered in the past, especially in physics 1, where we do the oscillations of basically a system of more than how should I say, a multi-body basically system oscillating. Anyway, so let's deal with that problem. Problem 51 says basically consider a CO2 molecule as shown in figure 4210C. So basically if you look at that picture, so we're doing 51 now, what you have in this case, you have an oxygen atom, then you have a carbon atom, and then you have another oxygen atom. This has a mass of oxygen, this has a mass of carbon, and this has a mass of oxygen. And you basically model this one as some sort of a coupled system. There is a constant in here, and for the spring constant of K. I know the book uses K prime, I'm going to stick with K. And there is another K in here also that models the interaction between the carbon and the oxygen molecule. So there is another K in here. So this is going to be X1, this is going to be X2, and this is going to be X3. The different locations of these different atoms outside of the equilibrium. So when this is oscillating, x1 and x2 and x3, they will go in every which way that you can think of. Okay. Basically, this is the model that we're going to be using. It's a mass spring system, and we're going to use F equals to ma for that problem. For this one, if we look at this x1, basically displacement of the oxygen atom on this side, it's compressing the spring by an amount x1, but the spring actually is being elongated on the other side by x2. So the net contraction in this case, the net compression in this case, is going to be the difference between how much we compressed on one side and the relaxed from the other side. So from the vantage point of this mass, it's going to look at it as being compressed by an amount x2 minus x1. For this mass M2, when it's moving on this side, it's compressing this spring next to this side by an amount again of x2 minus x1. So it's going to be x2 minus x3, I'm sorry, and it's also pulling on the other spring by an amount of x2, but it's being compressed from the other side by x1. So there is a pull by x2 minus x1. So this is basically how you model it. It's compressing on this side by x2, but it's being elongated from the other side by x3. So the net compression in this case is x2 minus x3, and the net elongation, because it's pulling on this spring on this side in here by an amount x2, but it's being compressed from the other side by x1. So the net elongation in this case, due to the displacement of the carbon atom, is this amount on this side. So this is, you need to keep in mind. Obviously, you have to multiply this net compression and net elongation by k to find the force due to Mr. Hooke's law. Basically, that's how we're modeling it. In this side, for the last molecule in here, it's being elongating the spring by an amount x3, but remember that this carbon atom is basically compressing it from the other side, so there is a net elongation by x3 minus x2. Oops, x2. Okay? And again, if I apply Newton's law, so this is, think of it, your free body diagram, there are two forces in this case. The force is this way, which is minus k times this number. And this force in here, this is going to be pushed by this way because it's compressing the spring this way by minus k times this number, and it's actually dragged this way too by another k times this compression, so both of them on this side. Now since this is moving this way, this is actually being pulled to the other side. In other words, everywhere the masses move, the springs will push or create forces due to Hooke's law in the opposite direction in this case. Okay, so this is basically the displacement from the equilibrium of the entire CO2 molecule that we're modeling in this case. And if I apply Newton's laws for the oxygen on this side, it's going to be m oxygen times x1 double dot is equal to the forces on it, which is in this case minus k times x1 minus x2. And in the same time, if I apply on the second one, which is the carbon atom, it's going to be mxw dot, which is mass times acceleration, is equal to the sum of the two forces. So I have on one side minus k times this side, which is x2 minus x3. And in the same time, I have also k times x2 minus x1. And finally, this is the last one in there, which is O, which is also the same mass, MO times x3, which is the mass times acceleration of the last atom, is basically equal to minus k times the total basically elongation of the spring, which is x3 minus x1, 2. This is the typical coupled system in this harmonic oscillators, basically, that are coupled, and you can break them down into their different kinds of modes. So I'm going to, basically the book in here, what it says in here, model each and every one of them as some sort of a cosine omega t and basically work out the problem. So instead of doing that, I'm going to do the general problem in this case because it's a little bit easier. So what I'm going to say in here, I'm going to assume that there is a solution of the form x1 exponential of I omega t. Obviously, I'm just taking the real part of this because we don't need to have complex numbers in here. But I'm just introducing them for convenience. So it's cosine, if you like, omega t. x2 is going to be x2 times the exponential of I omega t. And again, I'm looking for modes in here of oscillation. And x3 are going to be x3 exponential of I omega t. Potentially, x1 and x2 and x3 might be complex numbers, but there is no need for that if we're taking the real parts of every one of them. And since this does not involve the first derivative, so there is actually no need for that. So anyway, So if I take the second derivative from this expression, it's very easy to see that x1 double prime is going to be minus omega squared x1. And also if I take the derivative of this one twice, the first time we're going to put an I omega, the second time another I omega, so it's going to be minus x omega squared. And this is finally is going to be x3 double dot, which is equal to minus omega squared x3. So basically the problem becomes an algebraic problem instead of being some sort of a differential equation problem. Now, the exponentials will cancel when I sub all of that stuff, so I'll be left just with the arguments in this case, which are supposed to be constants, and that is going to give me the different kind of modes that I'm going to have for my oscillators. There is a useful definition in this case. I'm going to define omega naught or omega O squared as just being k over m of the oxygen, and omega carbon in this case squared is going to be just k, the spring constant, divided by the mass of the carbon. Okay. So in terms of these quantities, if I take the first equation divided by m naught, I will pick up an omega naught squared in this case. And if I divide the second equation by mc, again I'm going to pick up an omega c squared. But don't forget, I have two terms in here. I have an x2 in here and I have an x2 in here. So I have two of them. And I have a minus times minus, that's a plus, and a minus times minus, that's a plus. And in here I have again k over m naught, which is omega naught squared. So if I work out the algebra and move things to the other side, I will have a term with an x1. One of them will have a negative omega squared, and the other one will have, when I move it to the other side, a positive omega naught squared. So this term looks like omega naught squared minus omega squared times x1. Okay? Plus another term which has a minus times minus, that's plus another omega naught squared. When I move it to the other side, it's going to be negative again. So it's minus omega naught squared. And there is no mention in here of x3 in the first equation, so I'm going to place it with a 0 in here. Obviously, I'm going to write it in a matrix form. Okay? If you guys are not too familiar or didn't take linear algebra, please let me know, because this is, we can write it algebraically easily too. There is no difference, and it's just a convenient way of writing this expression, that's all. Anyway, so that's basically what I did. All I did was I'm just writing the first equation in terms of x1, this argument. I get rid already of the exponential. Okay, if you really want to go step by step, you're going to put an exponential in here and cancel the exponential, and basically you have an algebraic equation for the arguments of this substitution in this case. Okay, now, as I said before, this does not involve the first derivative, so we really don't have to worry about complex numbers. So this x1 and x2 and x3 could very well be real, and at the end we'll just take the real part of this expression and we'll have the solution for our system. We really don't care about that, honestly. We care just about the modes of oscillation. So, and that's the question in here that is asked for this one. In here we have another term in here. I'm going to move x1 times minus minus, so it's going to be a positive. When I move it to the other side, it's going to be a negative. But I have k over mc, so it's an omega naught c, omega c squared, I'm sorry, with a negative sign, multiplying x1. For x2, again, I have minus k over mc, and I have a minus k over mc, so I have two of them, and that is minus 2 times omega c squared. When I move it to the other side, it's just going to be a positive number, so it's positive 2 of them. I'm not going to write the plus because I know it's going to be positive. I don't want to be confused that this is some sort of a... So 2 omega c squared minus, again, this term in here that involves omega c x2. So that is going to be, again, 1 times... so it's going to be just another omega squared in here. Omega squared. And in the same fashion, I have actually an x3 term in here, which is a minus minus, so it's going to be a positive. When I move it to the other side, it's going to be a negative. And again, k over mc, that is exactly omega c squared. So it's going to be negative omega c squared. The last equation does not have an x1 in it, so I'm going to sub it for 0 in here in this term. And it has an omega 2 in it, it has an x2 in it, which is a minus minus, so when I move it to the other side, it's going to be minus again. So it's going to be minus omega naught squared again, or omega O for the oxygen in this case, minus omega O squared. And then the other term I have in here, it's an omega O squared, or omega naught squared for the x3, minus again this omega squared. So it's going to be omega naught squared minus omega squared. This matrix times this vector is equal to 0. The only way for this one to be true if the determinant, obviously we don't look for solutions where x1 is equal to x2 is equal to x3 where they are 0, because that's the equilibrium. We want something where this actually molecule is somehow vibrating or moving somehow. So that means that not all of them at once equal to 0. I mean, they could be two of them or one of them be 0, but not all of them 0, because that's a trivial solution. That's the state of equilibrium. So we need the determinant of this matrix to be 0. The determinant of this matrix is this term times this determinant, minus times minus, that becomes a positive omega naught, times this determinant, which is just these two terms. Okay, so that is kind of easy. No, I'm sorry, it's this term times that term. What am I talking about? Okay. So I have to be careful with this determinant, because it could lead to some disaster if we are not careful with it. So omega naught squared, omega squared, times, open big parentheses, these two terms. Okay. 2 omega naught c squared minus omega squared. If you don't like matrix version, it's similar to just basically go ahead and sub the values and work out the algebra and everything else, and you're going to have 3 equations with 3 unknowns, and the only way for those 3 equations that have 3 unknowns to have 0 on the other side, if again at the end the determinant will be 0. So this is identical to that one. So the product of these two, minus times minus times minus, so it's a minus actually. What is the mouse? Minus again omega naught squared omega c squared. Okay, so now we need to close actually these parentheses. Okay, plus this term minus minus, so it's going to be plus omega naught squared, open parentheses. I have this term which is minus omega c times this whole thing, so it's minus omega c. So I'm going to put it in parentheses, times omega naught squared minus omega squared. The purpose is to solve this equation, and this equation is of the power 6 actually in terms of omega, because if we find an omega, we found the solution. That's basically what this whole substitution is all about. Obviously this is going to be complicated, but it's already, we see that there is a common factor, omega naught squared minus omega squared, and omega naught squared common to the whole thing. So I'm going to take it out, and we already have a mode with that, which is omega equal to omega O. Omega squared. So the first two terms I'm going to expand them, because it looks like we have a disaster also if we are not careful in here in the expansion. So I have 2 omega c squared omega naught squared, so I'm going to take it in the habit of writing omega naught squared first and then omega c squared, plus, or minus I should say, 2 omega c squared omega squared, these two terms, plus minus omega naught squared omega squared, minus times minus, that's plus omega to the power 4, minus omega naught squared omega c squared, which is one of them is already here, which is going to be cancelled. That's important, that we really need to get rid of it. Minus times plus, that's minus, and this term is already out, so it's going to be minus another omega naught squared omega c squared. So this term and this term cancel this term, and that's very important because we really need to solve this equation, and one of the solution, it has to be omega equal to 0 actually. And I have omega to the power 4 in here, I have omega squared in here, I have omega squared in here, so I'm going to take it out as a common factor. So we'll end up with omega squared times omega naught squared minus omega squared times, again in here I have omega squared minus omega naught squared minus 2 omega c squared. The whole thing must be equal to 0. Obviously the 3 solutions are clearly omega equal to 0, which is very important mode. The other one is omega equals to omega naught, and the third one is the one that they are asking us about, and that is omega is equal to the square root of omega naught squared plus 2 omega c squared. So those are the 3 different frequencies that we have. This one simply means, if I put omega equals to 0 back into this equation, omega naught squared times x1 minus omega naught squared times x2 is equal to 0. That means x1 minus x2 is equal to 0. That means x1 is equal to x2. The last equation will also give me minus omega naught squared times x2 plus omega square naught squared times x3, because omega is equal to 0 is equal to 0. That means that x2 is equal to x3. So this one actually gives us x1 equals to x2 equals to x3, and that means the entire molecule is shifting one way or the other in space. So the entire molecule is moving completely with no vibrations whatsoever. And that is because t is equal to infinity, because t is 2 pi over omega, which is infinity. So it's non-periodic motion. The entire molecule is shifting left and right. So this is a non-important basically mode. This mode, omega equals to omega naught. So this expression is 0 when we sub omega equals to omega naught. So this will become omega naught squared minus omega naught squared, which is 0 times x1. So that is going to be left with minus omega naught squared times x2 is equal to 0. So this leads to x2 is equal to 0. And as a matter of fact, it's the same thing like the last equation that gives me x3 is equal to 0. X2 is equal to 0, I'm sorry, because this is x3 times 0 plus minus omega naught squared times x2 is equal to 0. So this is the case where x2 is actually equal to 0. In other words, the carbon is sitting still, and the other two atoms must be oscillating versus one another. As if the carbon is sitting still, the carbon is going to be sitting still, and this one, when it goes this way, the other one will go this way by the same amount. Let's check if they do. If we look at this expression now, we have omega naught is equal to omega c, and if we check this expression, because x2 is 0 now, so what we will be left with minus omega naught minus omega c squared times x1 minus omega c squared times x3. Take minus omega c as a common factor, and you will be left with x1 plus x3 is equal to 0. Indeed, if this one moves an inch to the left, the other one will move an inch to the right, and vice versa. If this one moves an inch to the right, to the left, I'm sorry, to this side, the other one will move to the other side, and basically they are moving against one another. So this is where the case where the carbon is sitting still and the other two atoms are oscillating, and they're oscillating with omega naught, because then in this case the carbon does not enter into the equation whatsoever. That is not the mode that they are asking us for. They are asking us for this mode. In this mode, it's a little bit complicated in the sense that we should see that the two oxygen atoms will move one way and the carbon atom will move the other way to compensate for their motion, and there will be oscillations. And that is the mode that they want us to find. So let's see that. Let's see if this is exactly what it's going to give us. Again, we're going to take one of these equations. It doesn't matter. So we're going to take this equation, omega naught squared minus omega squared times x1. So I'm looking for the last mode, okay? So we have omega squared is equal to omega naught squared plus 2 omega c squared. So if I sub in the first equation, what I have in here, I have omega naught squared minus this number. So I have minus 2 omega c squared times x1 minus omega naught squared minus omega naught squared times x2 is equal to 0. The last equation is going to be identical, except it's going to link x2 and x3 together. X2 and x3, yes. So it's going to be minus omega naught squared times x2 minus, again, I have omega naught squared minus omega squared, and omega naught squared minus omega squared is just going to be minus that twice that number. Minus 2 omega c squared times x3 is equal to 0. Obviously, if I solve these two equations together, x2 and x3 must be the same, because x1 and x3 must be the same, because if I subtract the equation side by side, this they will cancel, and this will give me identically that x1 is equal to x3 is equal to minus, solve either one of them, so it's going to be x2 times or omega naught squared over 2 times omega c squared times x2. Remember, x omega naught squared by definition is somehow k over mo, and omega c squared is k over mc. So this is going to be actually, mc will go all the way to the numerator, and mo is going to be in the denominator, because omega naught, if you sub the values basically, the k will cancel. So we're looking for omega naught squared over omega c squared. That's what we have in here. And that is going to be mc over mo. Okay? don't forget the factor 2 in here. So this is going to be exactly minus C over MO times 2 times x2. In other words, if I am concerned with the center of mass of the system, first of all, overall, the center of mass is given by M1 x1 plus, which is in this case mass O, plus M of carbon times x2 plus mass of oxygen times x3 divided by the sum of the masses. Now this equation tells me that x1 is equal to minus this number divided by 2. So when I multiply it by MO, the MO cancel, and it will be left in this numerator minus MO times this number, because x1 is equal to x3 when you solve these equations. So it's going to be MC divided by 2. So it's going to be minus MC divided by 2 times x2. I sub the x1 by its value from here, and MO cancels the MO because I have an MO in here, plus the second term I'm going to leave alone, x2, plus the last term. The last term also has a minus in it too, because that's x3. x3 is exactly equal to that one times MO, times in this mass, the mass of the oxygen. MO cancels the MO, and it will be left also with an MC over 2 times x2. So the numerator is actually 0, indicating that the center of mass also doesn't move in this situation. So the center of mass in this case also doesn't move, and the center of, and it's sitting actually on x2 in this case, because if the oxygen on the left moves slightly one way, the other one will move to the other way, so that stays in its place. This one too is the center of mass does not move, but all three molecules, the three atoms move in this case. But they move in such a way that x1 and x3, they will move together in one direction, in the same direction, to compensate for the motion of the carbon atom in the opposite direction. So this is in a nutshell basically what this mode is all about. Okay, that the center of mass doesn't move, and which way the oxygen move, or the carbon moves, the other one moves in the opposite direction. So basically this is in a nutshell the mode that they want us to find. So they said using the experimentally determined spring constant, which is K equal to 1860 Newton per meter, and the atomic mass for carbon is 12 U, and the atomic mass for the oxygen basically atom is 16 U, where U is 1.6605 times 10 to the negative 12. Determine the oscillatory frequency, which is omega over 2 pi. Okay. So the first thing is basically we're going to find is in this case omega, which is going to be square root of omega naught squared, which is just K over the mass of the oxygen, plus 2 times K over the mass of the carbon. And if you want to express in terms of the reduced mass, you could too, because the common denominator is MO times MC. MOMC, and the sum of the masses is going to be, and then basically I have MC plus 2MO times K. Okay, and this is the reduced mass, so MR in this case is going to be simply MOMC. By the way, this is omega naught squared, as we defined it all the way up there. Where is it? This way. And this, the other one is omega carbon, but I have 2 of them in the expression that we found. I have 2 in here. So that's where that 2 is coming from. And that's exactly the reduced mass. So the reduced mass in this case is just this number, MO plus M2 times MO plus the mass of the carbon. So let's plug in the numbers in here. So we have 16U times 12CU divided by 12U plus 32U. Cancel one of the U's, and it will be left with the reduced mass as 12 times 16 times the U divided by what, 44. So this is going to be some number in here, so I'm going to use the calculator. What is it? Let me move it to this side to look at the numbers that we have in here. So we have 12 times 16 times 1.6605 10 to the negative 27 divided by open parentheses, no, there is no open parentheses, 44. Okay, so it's 7.24 245 10 to the negative 27 kilograms. And don't forget you have the K in there. From there you're going to find the omega, and from here you're going to find F. F is going to be 1 over 2 pi times the square root. Don't forget that this is in the denominator, so it's square root of K over MR. So it's 1 over 2 pi square root of 1860 divided by this number under the square root. So I'm going to plug in the numbers, and you guys are supposed to check my numbers anyway. So the frequency in this case is going to turn out to be, let me write the square root first, of open parentheses 1860 divided by open parentheses again of this expression. I'm copying it, okay, basically so that I don't have to type it again. Close one parenthesis, close second parenthesis, and divide the whole thing by 2 pi, open parentheses 2 times pi. Okay, and the frequency that I got in here is 8.0636 something 10 to the power 13 hertz. It's a good idea to look at this frequency to see if it makes sense to you, and the only thing I can think of is in terms of the wavelength, and the wavelength in here is supposed to be lambda is supposed to be C over F. This is the dispersion law. So if it is really infrared or not, because we really need to make sure that it's not in the visible region or anything like that. So I have 3 times 10 to the power 8, that's the speed of light, divided by open parentheses, and it's going to be the same expression that I have in here. And it looks like it because, come on, this thing froze. Because I have 10 to the power 8 in the numerator, and I have 10 to the power 13. So it looks like I have the proper order. Okay. So yeah, it's 3.7 micrometers. So this is of the proper frequency. Remember, it's not in the nanometers or anything like that. So this is long enough wavelength, so it's fine. So this is problem 51. Problem 49. Man, it's already half an hour. Sorry guys. So I'm not gonna pause right now because I want to really get this thing out. So please, if you don't understand or have questions, please don't hesitate to ask. So again, the problem that I think we need to do is problem 49. So let's do that quickly. Actually, that cannot be done quickly, so I'm sorry about that. Okay. So let's see how is that going to look like. So what we have in here is we have a circuit where we have potentially an AC current. That's basically what we use this for. So we have an AC current in here, and we have a resistor in here to protect the diode, and then we have a diode in here. This is how the diode is represented, and it has a current flowing through it, I, and of course we have closed circuit in here, and this is the output voltage in here, so this is V out. Okay, now the triangular symbol with the lower edge is a diode such that a forward bias drives the current downward. Use equation 42.222. So basically, we're doing problem 49, guys, if you want to follow through. So it's going to be I is equal to IS exponential of EV over KBT minus 1. This is why I'm not using K. Is K prime everywhere because I use K for the spring constant, and in here I use Boltzmann constant. So this is basically Shockley's expression for the current as a function of voltage in here. For this one, that's the expression that I want to use. A typical value for IS, a saturation current, to being, what is my mouse? It's IS equals to 5 times 10 to the negative 13 amps. Okay, that's fine. Use a temperature of 300 Kelvin, which is room temperature. Okay. Any predicted current less than 1 microamp can be considered a zero current. Determine the minimum voltage V out for which the current I exceeds 1 microamp. Okay, so we need a voltage where this current I exceeds 1 microamp. Okay, so we need to solve this equation basically. 5 times 10 to the negative 13, or inequality I should say, 5 times 10 to the negative 13 amps times exponential of EV over kBT minus 1 is greater than 10 to the negative 6 amps. Okay, obviously I'm going to acquire that this exponential of EV over kBT minus 1 is greater than the ratio in here, which is 10 to the negative 6 over 5 times 10 to the negative 13. Multiply this by 2 and this is by 2. So 2 times 5 is 10. 10 to the negative 13, that's 10 to the negative 12. 10 to the negative 12, raise it up, it's going to be 10 to the power 6. So we need this number to be more than 2 million basically. So we need this exponential of EV over kBT minus 1 to be more than 2 times 10 to the power 6. Well, the one doesn't matter then if you have things that are more than 2 million. So exponential of EV over kBT must be greater than 2 times 10 to the power 6. Okay? It would be fun if you plug in the numbers of 1,999,999. That's nonsense. Okay, so if it's more than 2 million, it's good enough. So EV over kBT must be then greater than the natural log of 2 times 10 to the power 6, which means that the voltage must be greater than kBT over E times the natural log of 2 times 10 to the power 6. Don't be scared with this big number because it's not big when you take its natural log. So the answer is going to be kBT is 1.38 times 10 to the negative 23. So that's KB, I'm sorry, times 300 times the natural log, open parentheses, of 2 times 10 to the power 6, close parentheses. The whole thing is divided by, open parentheses, 1.602 times 10 to the negative 19, close parentheses. So if we solve this one, this whole expression is 0.375 volt. So anytime the voltage exceeds this amount, I rounded this number to 349. Okay, anytime the voltage exceeds this amount, you have a current that is already higher than a micrometer, so it's going to be detected. Okay, so you want to be careful with the voltage here because there is an exponential dependency in here. Okay, the current increases dramatically for diode voltages that exceed that value. At the given diode voltage V out, the diode has an effective resistance which is given by Ohm's law basically. Okay, so if I can measure the current through it and if I can find the voltage across it, so that is basically an Ohm's law. But it's, don't forget it, this is not an Ohm's law, this is just an effective resistance in here. Okay, given by that one. So basically RD is given by V out, the one that you measure, divided by the current running through it. Okay, to estimate the diode V out, use equation 42.22 to estimate the voltage via V out to equal to maximum voltage for RD equals to 100 ohms. So here is the deal. RD is 100 ohms. So that means the voltage is equal to 100 times this current, which means that the current must be then given by V over 100 ohms. Okay, and this must be given by the expression IS equals to exponential of EV over kBT minus 1. Okay, and the parentheses, of course. So where is that? Then I'm losing the mouse in here. Okay, so I need to solve this equation, and this is not an easy equation to solve. I basically like that. So, but I'm going to I have 5 times 10 to the negative 13 times 100, so it's going to be 10 to the negative 11, is equal to E over to the EV over KBT minus 1. And this whole thing is equal to, you cannot solve it really analytically, because this exponential on one side you have a linear function, on the other side you have an exponential function. So we're going to use it graphically. So what I'm going to say in here is, I'm going to graph the function x over 5 times 10 to the negative 11, and I'm going to graph the function exponential of e. So I need to find what this e over kbt is. Okay, e is 1.6 times 10 to the negative 19 divided by kb, which is 1.38 10 to the negative 23 times 300. So I'm going to find what this number is, because I want to multiply that by x, and the whole thing is minus 1. Okay, and graph that one. So again, 1.602 10 to the negative 19. The answer is going to be in volt, of course. Okay, whatever we find is going to be in volt if we're going to solve this equation, divided by 1.38 10 to the negative 23 times 300. And that is going to give me 38.695. Okay, that's close enough. And the exponential, so 38.695 times x, because remember this whole thing is. So I'm going to plot these two functions. So let me pull my calculator in here. Okay. Oh man, I crashed. Okay, let me get my mathematics again. Mathematics. Okay, so let me put it this way again. So what I want to graph is the following function. I don't know if you guys can see this function or this stuff or not, but let me see. I'm graphing y equals to x over 5 times 10 to the x over, open parentheses, 5 times 10 to the power 11, close parentheses. So this is the first function I want to plot, and I want to plot the second function, which is y equals to e to the power 38, I'm sorry, to the power, open parentheses, 38.695, yeah, 695 times x, the whole thing minus 1. Enter. Obviously it's going to give me some basically graph that I'm not going to be able to even read, so I need to change the range in here. And let me go to the plotting range. If you're not familiar with software in here, I'm going to go from 0 to 1 in the x-axis. I'm going to go from 0, because I need the positive voltage. Or what is the maximum voltage in here that I'm going to have? 10 to the power 20. That's too much. I know that the maximum voltage is going to be around 10 to the power 11, because that's how the on one side it looks like. Okay. So that's 10 to the power 12 is 11 is too much. Okay, so I'm going to go all the way to 10 to the power 10 instead, because I don't see this. So in here it should be 0. And in here, home, and so 10 to the power 10. Okay. I'm not seeing the trace in here to be able to find a trace. 10 to the power 9, maybe. Plotting range from 0.37 all the way to 0.7. Home from 0 actually. Why do we get this number? I see the line in here starts to move, but I don't see plotting range again. Let's move it from 0.5 0.9 times 10 to the power 10. Power 9. Okay, except we know the solution is not anywhere in here, so we need to go in higher in the range, because probably where they are meeting it's way up there, so I need to go higher in the range. So in this case it's from, because I'm going from 0 to this number, so I need to go from, hold on, home, so I'm gonna go from 10 to the power 10 all the way to 10 to the power 11. Okay, the problem was the function itself that I wrote in here has 10 to the power positive in here, and you can go back in the video and you see that I entered that one wrong. Okay, so I fixed that when I went back to my notes, and now I can clearly see that these two lines will meet, namely the one side of the equation meets with the other one, and I actually do a trace in here. Where is the trace? I can do a trace and find where they meet actually, and they meet in the point 0.6 for the X, for the voltage. Okay, and that's the main thing. X is the voltage, so that is a similar numerical solution. Okay, where is my notes in here? So a numerical solution, the voltage must be 0.6, and this is typical, by the way. Okay, so where is my pen in here? So the voltage V is 0.6 volts is the solution for that. And so what is the question again? I lost myself in here and there. To estimate the diode voltage V out, so this is how much the voltage V max that you can have, which is 0.6 volts. Okay, so V out at most V out is going to be maxed at this number. Okay, because that's the maximum resistance that you basically are going to assume in here, which is 100 ohms. After that you're going to damage your diode. To estimate the effect of whatever, so we found it. What is the diode voltage V out max for the RD equal to, okay, we did that. What is the diode, what is the current in that case? Okay, so we know what the voltage is, and this is gonna behave like an ohm resistor now. So this is just being like equal to 100 times the current I, and this is basically the current in this case is going to be 0.6 divided by 100, or 6 times 10 to the negative 3 amps, or 6 milliamp. So that's how much current is going to be at that point. Okay. If the resistor R is greater than 10 kilo ohms, then RD is a lot less than R. So this R now is 10 kilo ohms. Remember, this R is 100 ohm. Okay, I mean for roughly, okay, this is a number that we want to find the current with the maximum voltage. So usually R for the diode is a lot less than that resistor in there. Okay. For larger currents, and there is negligible additional voltage drop across the diode. This effectively pins V out to be a maximum voltage V for all voltages Vn greater than Vmax. With this perspective, estimate how this current with respect to sinusoidal. Okay, so if there is a large current in here, large voltage in here, where this is the positive and this is the negative in here, so all of the voltage drop, because it tries to drive a huge current, is going to happen in here. So this is the voltage drop for the most part. There is a small voltage drop of 0.6 volts is going to happen in here, so all the current is going to happen in this case, and the V out will be exactly the Vmax in this case. If the voltage now is not very large, in other words, there is a small current, so in this case, or it's reversed, so then in this case the V in this point in here is going to have a very small current, and that small current will be read in here. So this is basically how the diode would be working in this situation. So let's jump to another problem, and that is problem what did I say? Which other problem I promised that we need to cover in addition to the ones we just did? Problem 41. Okay, problem 41. This is similar in a sense to problem 52, which means that you guys really need to think about this kind of problems in here to that you might be asking about it some other time in the future. So the hydrogen iodide, which is HI, this is problem 41 by the way, HI molecule has a separation of R0 of 0.16 nanometer. I mean, they have an extra 0 for sig figs, that's all. And vibrational frequency, so the frequency for vibrations of 6.93 10 to the power 13 hertz. I already checked something of the same order of magnitude, and we found it to be in the micrometer range, so this is fine. Okay. The mass of a hydrogen atom is, so this is how the molecule would look like. You have a hydrogen in here, which is usually on this side, and you have the iodine in this case on this side, and the separation between them is R0, and the masses are given. So this mass is 1.67 10 to the negative 27, and this mass is given 2.11 10 to the negative 25 kilograms. Okay. Calculate the moment of inertia of the hydrogen iodide. Okay, well, in this case it should be straightforward. First of all, we need to find the reduced mass. Yeah, that's what they asked for. Sorry. Yeah, we need the reduced mass, so because we want to find I, remember, is equal to the reduced mass times R0 squared. This is from the theory. And reduced mass in this case is just equal to the product of the two masses divided by the sum of the two masses, because it's a diatomic gas and diatomic molecule. So the reduced mass in this case is, just plug in the number 1.67 10 to the negative 27 times 2.11 times 10 to the negative 25 divided by the sum of the masses, 1.67 times 10 to the negative 27 plus 2.11 times 10 to the negative 25. Man, and this whole thing times R0 squared, and R0 squared is just this number, which is 0.16 times 10 to the negative 9 squared. I'm going to plug in all of this for the moment of inertia in the calculator. Hopefully it doesn't crash on us again. So let me pull it, and I need to go to the calculator mode. Okay, so in the calculating mode, what we have in here, we have the R0, which is open parentheses 0.16 10 to the power negative 9. Okay, the whole thing squared, not 23. Okay, times the product of the masses, which is 1.67 times 10 to the power negative 25 times the other mass, which is 2.11 times 10 to the negative 25, okay, divided by, open parentheses, the sum of the two masses, 1.67 times 10 to the 10, what am I writing, 24, 10 to the power negative 27 plus 2.11 10 to the negative 25. Okay, so this is the whole thing. Okay, we have the reduced mass, we have the distance separation squared, and we plug in the numbers, and it's giving me 4.24 times 10 to the negative 47, and that's a typical number. Okay, 4.24 times 10 to the negative 47 kilogram meter squared. Okay, so that is the moment of inertia. Okay, B. Calculate the wavelength of the photon emitted in each of the following vibrational transitions. First of all, we need that expression for the energy of vibrations and rotation. So in this case, what we have is the energy is quantized, and it's given by E and L. So for the rotation, I have this expression times h bar squared over 2I plus n plus 1/2 times h bar omega. But remember, h bar omega is h over 2 pi times omega, and omega over 2 pi is f. So this is hf. Okay, so this is actually h times f. Okay, f is the frequency that was given to us to be some number 6.93 times 10 to the power 13 hertz. Okay, and h is just a constant. Okay, so we want to transition between n equals to 1 and L equals to 1 down to n equals to 0 and L equals to 0. So this is fine in terms of the we have a change in n by 1, and that is actually going down. So this is an emission spectrum, and we have L going from 1 to 0, which is delta L is equal to plus or minus 1. So that is a conservation of momentum. So the final energy is going to be this one, and the initial energy is this one, and the frequency that is going to be in this transition is going to be equal to, the energy. So it's going to be L is equal to 1. So it's 1 times 1 plus h bar squared over 2I plus n is equal to 1. So it's 1 plus 1/2 times hf minus the final energy where it settles down. So that is L equals to 0. So it's going to be 0 times h bar squared over 2I minus, for n equals to 0, 0 plus 1/2 times hf. This 1/2 and this 1/2 cancel, and this is 0 anyway. So I have 1 times 2 times 2, so it's going to be basically the energy is going to be h squared over I plus hf. Okay, I'm not going to do the calculations right now. I'm going to do it shortly after I get the other two transitions, okay, because they gave us 3 of them. The next one is between n equals to 1, so we're going to call this one E1 actually, just to plug it in the calculator. So we have n equals to 1 still, L is equal to 2, going to n equals to 0. Again, this is an emission because n is more than the final is less than the initial, and L is equal to 1. Again, this is allowed by the selection rule because L changes by 1 and n changes, in this case doesn't matter, changes by 1 in this case, yes. Delta n has to be at least equal to 1. Okay, so what do we have in here? Okay, so in this case E2, I'm going to call it E2, the second basically transition. So what I have in here for n equals to, let's start with L equals to 2. So we have 2 times 2 plus 1 times h bar squared over 2 I plus n is equal to 1, so it's going to be 1 plus 1/2 times hf minus In this case, L is equal to 1, so it's going to be 1 plus 1 plus times h bar squared over 2I minus, again, n is equal to 0, which is 1/2 of hf. This 1/2 and that 1/2 cancel, so we still have an hf in here. So this is E2. And in here I have 2 times 3, that's 6 divided by 2, that's 3. 3 h bar over I minus h bar over I. So it's going to be 2 h bar squared over I. Okay? So it's going to be twice this number, that's all. Plus the same thing in here. And the final transition is going to be between n equals to 2, L equals to 2, down to n equals to 1. So that's fine. That is actually so far so good. And L equals to 3. Actually, that's still valid in here because L changes by plus or minus 1. So in this case also that is valid. So in this case what we have in here, I'm going to call it E3, is going to be again the final state, the initial state, I'm sorry, because this is still an emission. So it's going to be 2 times 2 plus 1 times h bar squared over 2I plus, again, now we have 2 plus 1/2 times hf minus, in this case L is equal to 3, so it's going to be 3 times 4 times h bar squared over 2I minus, again, 1 plus, that's minus 1 plus 1/2 times hf. Always you have an hf in here, okay, because you have 2, so it's going to be just an hf in here. How about this numbers in here? So I have 6 divided by 2, that's 3, and I have 12 divided by 3 by 2, that's 6. 3 minus 6 is going to be negative 3, so it's going to be negative 3 h bar squared over I. And this is E3. So I'm going to plug in the calculator and we're done with this problem. So, what is my calculator here? I'm going to pull it to this side, so just to see what I have in here. So we have an h bar squared. Let's look at the first energy in here. So we have an h bar squared. Since I don't know what h bar squared, I know just what h is. So I'm going to write 6.626 10 to the negative 34 divided by, open parentheses, 2 times pi, close the parentheses, the whole thing squared. Okay, divide that by I, and I calculated it earlier to be this number. So divide by, open parentheses, this whole number, come on, plus h, no, not equal, plus 6.626 10 to the negative 34. Oh, maybe we should use the okay, we're gonna get it in electron volt by dividing the whole answer by E. So we're gonna get it in joule right now. Okay, times the frequency, and the frequency according to this problem is 6.93 10 to the power 13, and this is the energy in joules, is 10 to the negative 20. So let's divide that by the electron volt, by the electron, 1.602 times 10 to the negative 19. Okay, so this energy here is 0.288 electron volts. Okay, let's do the same calculation in here, where we multiply just that number by 2. And we're in business. Okay, and the answer, of course, has to be divided by, come on, by, again, 1.602 10 to the negative 19, close the parentheses. it's 0.289. Not much difference between the two. I guess we have to be very careful with these numbers because they are very close from one another. 28990, and the first one was 0.28827. Okay, electron volt. Okay, the last one is, the difference is actually this h bar squared, and the difference is coming from the rotational energy, and the rotational energy comes with an h bar squared, so it's still a very, very small contribution, okay, compared to the vibrational energy. That's why you see very little difference between these two. You double this number and it's still very small change compared to the overall energy. So and that's an important point actually. So let's look at the last expression where we have a -3 now, so it should not be really that different between this three numbers. So again, we're going to divide that number by, open parentheses, 1.602 times 10 to the negative 19, and close parentheses, and sure enough it's very similar to the other two numbers, indicating that the main contribution to the energy is coming from vibrational oscillations and vibrational energy. So it's going to be 0.28172 electron volt. Okay, so again, for the main contribution in this case is coming from the from this HF. Okay, the others are very minor contributions to when it comes to the energy, but they make a difference because when you look at the spectrum, you will see distinct wavelengths in here. Okay, if you're curious trying to find the wavelength for this energies, you just basically have to use convert back this one to joules, and use the fact that this is an energy that is given by H times a frequency, and you use C over lambda for the frequency. So it's going to be an HF divided by lambda, and HC divided by lambda. From here you're going to find what that C is, lambda is, and find the different wavelengths, and they all should be in the proper range. They all should be of the order of a micrometer. Anyway, this is the problems that I promised to do. I have problem 47 that I want you guys to go through it. If you have difficulty, please let me know. And I also have problem 38, which I want you to guys go through it. Problem 44 is actually a nice problem too. All of these problems should not be hard for you guys to do. And if you have questions, please let me know. Thank you.